Okay, so we're back here in the Security Ledger studios. I'm your host, Paul Roberts, back for another episode of the Security Ledger. And with us in the studio, we're really happy to have Boyd Multerer. Boyd is founder and CEO of Kry10. Really cool. IoT security startup. Boyd, you've got a really interesting history and a really impressive kind of biography. Tell the audience a little bit, our listeners a little bit about yourself.
It's really good to be here. A little bit about myself. I actually didn't come from a software background. I came from manufacturing and from factories and have a degree in mechanical. So I always thought I was going to be a mechanical engineer, but found myself drawn to the software part where there's like fast turnarounds. And as you go through a career of that, building first desktop publishing and then web servers and all that, you find yourself dealing with more and more security issues as we get more and more connected. So around 2000, I joined the Xbox team and helped build Xbox Live, and then XNA, which was a developer program, and then the Xbox One operating system. And the lesson you learn through all of that is that, you know, where you think you're going to build a stripped down PC that plays games, you actually end up building something that looks more like an industrial device that is real single purpose and focused on a certain area. And it's got both physical attack vectors and it's got software attack vectors. And it's just a very different mindset. And then after Microsoft and after all that, you reflect, and I realized, oh, wait, physical vectors, software vectors, it's all industrial. And there were patterns there that I could learn from.
Going back in your history, you actually started off focused on like the desktop publishing space, right? Pre-Microsoft.
Yeah.
How do you find your way to the Xbox team back in 2000, which was, I guess, probably the origins of Xbox as a product?
Sometimes careers look like a random walk, but then you realize they're not later on. Coming out of mechanical engineering school, I don't know, I saw flaws in PageMaker that I wanted to go help fix. So I wrote stuff that worked in desktop publishing. This is in the 90s. If you go look up old PageMaker books, you'll find me in them. And then I did some contracts with Microsoft and met Jay Allard about 1994. So he was busy trying to turn Microsoft into something that embraced open web protocols, HTTP. So that come 96, I'd already built up a relationship with Jay. And just about the time that Adobe came in and bought all this and all that happened, I found myself doing a contract working on IIS-3, which was Microsoft's first web server, early web server. And once you see that, you're like, oh, this is going to replace desktop publishing. Right? So core philosophy, you build for where the world's going and not for where it is. So I made a decision at that time. Web wasn't taking off yet, but I could see it would. So I dropped the desktop publishing, went in the web. And that was really fortuitous because 3 years later, Jay has spun up the young Xbox team. And he asked me to come in and go figure out, the way he put it was, after much debate, we put an Ethernet port in the box and not a modem. Go figure out what it talks to.
What was your answer to that?
You have to do the same exercise. Where's the world going? At the time, there was no broadband. It was like ISDN lines and really low penetration, but you could see where it was going. So let's go build a scale-out web service that's built for hundreds of millions of devices that are managed locally but can be configured. No, managed centrally but can be configured locally. We had to deal with attack patterns that ranged from hardware logic analyzers down to people trying to save games on storage media. So as soon as you go down that path, you find it's quite a deep hole.
That became Xbox Live, basically, right?
Yeah, it became Xbox Live. It had tendrils into the OS. What we did in 360 and Xbox One was then we took it a layer down even lower into the hardware. There's transistors in the SoC to support those systems going back upwards.
Right.
And that became really informative as to what are the techniques you use to protect industry.
One of the interesting things about Xbox is that the content on Xbox is highly valuable, right? So you've got these games that are very desirable and that are a population of people globally very interested in pirating them so that they can use them and run them for free. And that's always been the case same thing with music and film, right? This is what the DMCA was actually created to protect, was this type of content. Very valuable, very sought after.
There's two reasons people attack a game console. That's one
Yeah.
of them.
Yeah.
So one is to play free material or to get
Yep.
around paying licenses. The
Yep.
second is to cheat to win. And they're very different attack vectors.
Talk about how they're different.
In the play free content version, the attacker they're not trying to change the experience. What the attacker wants to do is they want to sell you a multi-terabyte hard drive with every game on it and sell it to you for $80. They're selling software by weight, right? So they're looking for physical attacks that can defeat the cryptography that checks that a game is valid, that checks that it is on valid media. The cheat to win, there's all kinds of different vectors that you could try to look at. Some of the early ones that we saw that were a little easier to defeat would be like a network sniffer. Maybe I'm running a perfectly valid game, but if I have a PC next to it and I can have a top-down view of where all the players are in the game, I get an information advantage. Or if I'm in a game and I'm losing, can I pull the network cable out of the wall and cause the session to fail and now it's not recorded as a loss? Right? All the way to people glitching hardware where if you drop the voltage on a pin at the right time, you can clear a register and that changes the values that are going through at a certain point in time. So that's much, much harder because you have very tight timing channels and requires a soldering iron.
Right.
But the set of things that you have to do are quite different between the two. So you have to really understand your threat model.
How did that affect your thinking as an engineer working on that team? Because most in the security space, you're usually, you might spend most of your career really focused on one type of threat actor.
Right.
Or a pretty small set of threat scenarios. But this is like constantly evolving. First of all, you're continuing to issue new consoles, right? And new games and new features. And then obviously each of those kind of spawns new attacks and new efforts.
Yeah. So how did it affect me? If you look at when we started with the career path, you start doing desktop publishing and UI work. And then you start working on web servers. And my role there was managing public-private key cryptography on the website. And then you start thinking about how to lock down a data center. And then you think about 100 million devices that are connected to it. How do you show that the kernel hasn't been patched? And then you start realizing, oh, geez, now I've got these physical attacks that are happening. And then those things are timing where they're actually measuring instructions. And next thing, you've got people working for you who are doing FPGA work and like blowing fuses and making sure you can't roll back. And you've got lots of keying. So it's been a constant education as you go. And now I find myself worrying about everything from protecting data once it's in the field to if you have a collection of devices and you're trying to manage permissions on them, it becomes a permissioning nightmare. Your attack vectors start to become human, right? Where if I can game the people putting permissions on because their job is too hard, now I can take over a set of devices without violating the rules, right? And you go from there all the way down to worrying about leakage across an L1 cache between applications. So Spectre and Meltdown are still things that we have to worry about and we have to design in as we're building systems.
Can we talk about just the Internet of Things space more broadly as it exists today? We've got tens of billions of IoT devices connected globally. Most of those are low value, low or no security devices. Get them to market, focus on features. And it's a real mess out there, security-wise. What are your thoughts on why that is, and where do you see the real kind of problems right now with the IoT deployments that are out there?
Let's start by looking at the shape of the IoT devices. What we think of when we say IoT, we tend to think of really small devices. Maybe they have an ARM M processor like an M4 or something. They do a single job. Maybe they have a single thread running. They don't even really have an OS. It's like a little RTOS thing. Read a piece of data, maybe take a simple action, maybe send some data up, and that's about it. For those devices, those will, they're battery constrained and they're cost constrained. And that's a class of device that will be out there for a long time, but we have to understand its limitations. What's interesting to me is the new class that's emerging right now, which is a bigger device. It's on minimum like an ARM A7, so it's got a proper CPU on it. It's got half a gig of RAM. It's got multiple threads, multiple applications, multiple jobs that are running at the same time. So think, I'm collecting data, I'm storing and managing that data, I have an AI model running. I may have a separate application, a second AI model running that's doing a different set of reactions based on it. And they have different update patterns, or my data collection can never stop, but I'm constantly resetting and updating the AI model. It's still a device in the field, so it's still got the shape of there's not a human there. It's in the field doing a job. And it's still true that the job it's doing is worth more than the device, but they are getting inherently more complex. And I personally think that many of the small IoT devices will start to go away. There'll still be a market for really little things, but they'll be connected to a bigger one, right? More of the logic will be running on the bigger one. And maybe that bigger one will be controlling like 10 or 20 of the small ones. So you have to think about, where's my logic running? And if a fault happens anywhere in the logic, and I don't care if it's an attack or if it's just an error or if it's a bug, what's the damage that fault can cause, and what are the consequences of that fault? Right. So really, you have to think differently. As soon as things get more complicated, you have to think very differently about how you isolate and how you contain and how you deal with the damage of a fault.
But my sense is those conversations probably aren't happening. Maybe they're happening in some contexts, medical devices, maybe automobiles, things like that. I don't necessarily get the sense that those types of conversations are happening.
That's because we're at the turning point right now. And
Okay.
I think as I've talked to people, we're already there. And not everyone sees it yet, but I'm surprised by the number of companies who have already had to contend with these things. Any place where you're collecting complex information and then making decisions based on it, where you have to update that decision matrix, are already there. And this could be true for a door camera that also unlocks the door to your house. It's definitely true in automotive. Massive, once in a generation shift happening in automotive right now. CPUs are basically going away and it's becoming a central computer. That central computer is a large, complex device where you have to isolate the components on it and worry about the damage that, how to put it, you don't want a fault in the radio to cause your safety systems to malfunction.
As with Miller and Balasek, basically.
Yeah, that's right. So you have to really worry about those connections, the isolation between components, although there's reasons now they have to be on a central computer, because as soon as you have high definition images floating around that you're doing analysis of, you need the bandwidth. You can't have it be on a local network, right? An ARM isn't going to cut it. You need A7, A8, A9, something higher.
Let's talk a little bit about Kry10 and sort of the origins of the company. Many of these devices that we're talking about are running on, as you put it, operating systems or platforms from the last century, which is absolutely true. Which is definitely true. Most of them are Linux or maybe even embedded Windows, depending on what types of devices you're talking about. And kind of general purpose operating systems. So talk about what you saw as the opportunity here and what led you to stand up Kry10.
So we'll talk a little bit about the story and understand that we're in a phase now where we've built a new thing, and sometimes it's hard to exactly describe it. So even we're landing on our language for exactly what is it. And I'll do my best to describe it to you. The first observation you have when you leave a company like Microsoft, you have to go and scan the world around you, look at all kinds of other tech, right? And I found two pieces of tech that were super interesting and that informed some of these decisions. The first one was the Erlang Beam, which is from Ericsson Corp. Beautiful piece of code. What they teach in the Beam, and languages would be like Erlang or Elixir, what they really teach is how to break your code up into pieces so that you do the minimum amount of work to recover from a fault. That's really what it is. And this is why telephone systems are all built on this thing, and they measure the uptime in decades. Like they don't talk about how many nines in a year. They talk about how many nines in a decade, and there better not be any. It better be 100. So they've shown how to build systems that you can update, you can keep them going, and you can recover from a fault without having the whole thing go down. At the same time, I heard about a piece of tech out of Australia called SEL4. Now, this is a microkernel. Now, this does go back to the 90s. Actually, so does Erlang. That goes back to 86. But the debate in 92 was, are operating systems going to go down a microkernel path or a monolithic kernel path? And in a monolithic kernel, drivers live in the kernel. So when you install like a printer driver, you have to put your password in. You're effectively acknowledging, yes, I really mean to install this thing because it's going into your kernel. If it crashes, your machine reboots. Right? There's no really good isolation. And yes, there's new advances in hardware to try and create some, but it's a big blob of code that is sitting there together with millions of lines from who knows where, running in the most sensitive part of your computer. So you take on a lot of risk when you have a monolithic kernel, but you gain performance.
Right.
Versus a microkernel, where you separate that risk, everything lives as an application, but now you have a performance penalty. And in 92, when it was Pentium chips, that performance penalty was a big deal. But now it's 2023 and it's not. Right? There's better intrinsics, they're faster, it's not 8,000 cycles that go between user and kernel mode, it's like 80. And chips are just so much faster. So that performance thing is no longer an issue. Now it's momentum. So when you think about devices, you look for areas where you get to have a reset conversation about what should an OS be. And in devices, there's not a huge amount of legacy there. Yes, people have written code in Linux, but that's more about the API than it is about the kernel itself. So you get to have that reset. You get to talk about microkernels. You get to talk about capabilities and ways of having APIs that you can refactor and you can build new things in. And then you look at latest pieces of tech, and the thing that really blew my mind was formal methods, which is if you have that microkernel, you have to believe it's correct. You have to believe it works. And the only way to do that is you use formal mathematics to prove that it's correct. And once you're there and you can believe it, you can start to do some truly new things.
So just explain for our listeners, when we're talking about formal methods, what are you talking about? You're really talking about mathematically proving that software works as it is designed to work and doesn't have behaviors that are not accounted for.
Yeah, that's right. So this is really about testing. This isn't so much about writing the code, it's about knowing that the code you wrote is right. In normal testing, you'll write a function and then you'll write some tests that call it with some values that should give a good answer, call it some values that should cause a bad answer, and then you check to see if you got the values you expected. And it's probably going to work if it does. But you didn't check every value. It would take a lot of time. So in formal methods, what they do is first they build they basically they build a specification for logic in pure math. And the tool they use is the Isabelle Proof Assistant, which if you haven't seen it, you should go look it up. It's fascinating. There's a language inside called Isabelle Hall called higher order logic. Okay. And you can literally write programs using mathematics. And it's not really programming, it's a proof. You're writing a proof in pure math. And that proof, the shape of the proof can describe logic. And then you can make claims about it because it is a proof. You can show, hey, there's no way this thing can buffer overrun. There is no way that there can be you can dereference a null pointer. There's no way you can do all these other classes of things. And then below it, you write C code to implement the spec. But because you're in math land, you can write a proof showing that the C code is a correct implementation of the spec. And then you write another proof that says, I don't trust the compiler. How do I know the compiler didn't inject it in an attack? Or how do I know the compiler didn't misinterpret my C code? So then you take the output of the compiler and you can prove that is a valid implementation of the C code all the way down. So now I've got a binary that runs on the machine that I know is a correct implementation of the spec, and I know that the spec has these properties. This is new. Effectively, what it does is it tests all possible inputs at the same time. Right? Like the thing that's exciting about quantum is it can like test all possible keys against an
Mm-hmm.
encryption algorithm at
Mm-hmm.
once.
Mm-hmm.
This effectively tests all possible inputs to a function at the same time. It's
Very
just
cool.
extremely hard to do.
And resource intensive.
Human resource intensive.
Human resource.
You need mathematicians who think about logic and can write this stuff. So the kernel that we use is SEL4, and that's the thing that's mathematically proven. And it has what's called a capabilities interface, which is beautiful because it's very composable. Right.
And so the advantages of using it for a company like Kry10 are that you can basically go out and assert that this is a secure architecture and secure environment.
Basically, yeah. There's always caveats. I have to assume the hardware works as specified. And effectively, what it allows us to do is we can create sandbox for other code. And those sandboxes are the things that are backed by the formal proofs. So I can load informal code. I can load normally tested code into one of these sandboxes, into a least privileged sandbox. It'll execute. And even in the event of a full takeover, someone has completely taken over the code and they fully own execution inside the sandbox, they cannot break out of the sandbox. That's the point.
Powerful.
Right. So now let's say I'm in a vehicle, and use a real example that happened in Seattle like about a year ago. Bad metadata comes down on a song that's playing on the radio. It caused the music app to crash. And it crashed in a way.
This is Toyota, is that, if I recall?
It was Mazda. It was my favorite
Mazda.
My old favorite radio station. Malformed metadata. The head unit crashed. It took the whole head unit down. That should not happen. It's fine if the radio player has an issue, but it can't take down mapping, and it can't take down your phone call and take down system control. Or those have to be isolated from each other, even though they're running on the same computer. So that's what we're talking about. Using the formal methods to back up that isolation.
So Kry10, this is, in some ways, you are on the front edge of, as you said, sort of an emerging trend. But most manufacturers are invested in the hardware and software and architecture that they've got. They might be looking to incrementally improve the security. You're really coming to them and saying, I'm going to shift the whole paradigm. Hard conversation to have.
A hard conversation, and it's hard to explain. For a company like us, what you look for is customers who are already at the point where they have a problem and they don't see a way through it. Right? So the shape is someone who's building a device that maybe used to be simple, but they're being forced to combine them onto one computer. Or because they're bringing in AI onto these devices, they're no longer simple. Like a lot of golf courses now, the lawnmowers that mow the lawn there's no human on it. They're like little robots that go around the whole thing and they mow the course and they come back to the barn and charge themselves up at the end of the day.
Sure. Yeah. Or has an autonomous tractor, right?
Yeah. How do you know that the mower control, the navigation control, the looking for humans walking around bits, the talking to the radio, the updating the communications back to home base, how do you know that they're not interfering with each other? How do you know that someone can't take it over? Vehicles of all kinds, when you're looking at cars as well, massive change. ECUs are shrinking the little real-time units, and the software that used to be on them is now components on a central computer. It's got that flavor, right? They need something new. So when I talk to car companies, the conversation is like, yeah, we have a problem. We can't use anything that's out there today. It was all built for this physical separation model, and now they're combined. We still need the separation. Yeah. So you look for places where there's a massive shift like that. Yeah. And that gives you a place to come in and have that conversation. If I tried to do this 10 years ago, I don't think the market would have been ready, but it is ready now. We're finding those conversations. And not everybody's there, but I think they will be.
What are the security benefits of this? When we look at attacks on IoT devices, most of them are not happening at the kernel level, right? These are trivial exploits of, software vulnerabilities, injection attacks, buffer overflows, that type of thing. That's a kind of boil the ocean problem. How do you get software developers to create more secure code? But will having a platform like Kry10's make the consequences of those more mundane security problems?
That's getting there. So as a platform, we want to make it so that if you're using our systems, and we care a lot about the tools and making it so it's really easy to get things started. As a developer, I always hated beginning a new project where you spend the first 3 days just trying to get the tools to compile. Right. I want this to say, hey, I'm building a new device and it spits out a system that's ready to start running. You just start adding your business logic. But the thing it spits out is by default built in a way where there's sandboxes that are defined by least privileges that you start putting your code into. Now, your code is still your code, and I can't help you be a better coder and all that, but I can contain the work you're doing and prevent it from affecting the next container. So really what I'm doing here is I'm trying to shift the conversation away from here's a bunch of apps and toward here's a bunch of risk buckets. I have containers that run code in them, and the point is that any one of these containers may have an error and it may go down and it may need to be restarted. I want to know that it can't cause the next container, the container sitting next to it, to have an error. Right? So you allow the system designer, the device designer, to start thinking in terms of pools of risk and where you put in your various bits of code. If, hey, here's a driver and here's some software, and if either one fails, they have to be restarted together, you might put them in the same bucket, right? But the more you can separate, the more you have the ability to restart into a known good state with minimum effort. I want updates, like the downtime from an update, to be in like the 100 millisecond range. I want recovery from an app failure to be in the 10 millisecond range. All right, already from a cold boot, because you've eliminated so much, even turn the power off and turn it back on, we're looking at like second, sub-second. So you change the nature of the discussion to be less about writing apps, which is a monolithic OS concept, and more about what's your risk containers and what are the connections between them. Because every time you allow them to talk to each other, that's the way risk can leak from one container to the other. So from a security perspective, it really changes the way you think about your device.
Who's your competition? Are you going up against the NXPs of the world, the chip designers themselves, the silicon designers themselves, or Intel's, or is this more of a I don't know, who's out there? Who is your competition?
Well, it's a great question. I definitely don't think it's the chip designers. Okay, we need the chips in order to run, and I view them very much as partners. Like, we run really well on NXP chips. Any chip where the proofs have gone all the way down to the ISA is something that we run well on. So we're like, today we're focused mostly on ARM64 and RISC-V 64. There's efforts going on to get the 32-bit versions working. I do x86 if there's enough devices that want to use them. It's about supply and demand, right?
Right.
When you think about other operating systems, like, who's the competition? You could say, hey, if we're about security, there's things that are about security. If you say it's about uptime, there's things that are about uptime. If you say it's about remote management, there's things about remote management. What you struggle with is to find anyone else who's really solving the combination of them. So I think what we're doing is we're defining a new category here. Devices that have a certain amount of flexibility and they have a certain amount of zero trust built into the architecture at a deep level. Who can do the updates? who's got the key material to authorize an update, that kind of thing, along with isolation for apps, but that isolation is defined by the person who has the key material. So not anybody can change who's got the permission to change which apps and which buckets and what those risk vectors are, has to be controlled all the way with cryptography up and down the stack. So it's a holistic view of it, and I don't see anybody who's really in there. If I had to say who's my biggest worry, it's complacency. And to me, complacency is defined as good enough Linux, as in, it's good enough, we'll just use it. Except when lives are on the line, or when your business is on the line, whatever the job the device is doing is on the line, then you realize, I'm not going to worry about it. It isn't good enough.
That is an issue because there's certainly been ample evidence that there are real security problems with the Internet of Things, that there is a vulnerable devices out there, potentially with kind of cyber physical consequences to failures or interruptions. And yet, maybe with the exception of the electric grid, we have not seen a robust policy response. I'm speaking to you from North America, United States. Certainly not a focused one. And I think that's true everywhere. Ultimately, companies often do things when they've got that regulatory kind of gun to their head and they have to do them. Do you see that as being the game changer, that type of thou shalt?
Great question with great timing. So right now, being debated is the European Cyber Resilience Act. This is game changing. This thing describes the consequences if you put out a device that you fail to update, if you put out a device that has known bugs in it. If you're not at the top of your game and that device fails and someone dies, your board has liabilities. It actually goes further, and this is where more of the controversy is. If you contribute to open source and your contribution has a flaw in it and you don't bother to fix it and someone else dies because of that, you might be liable. So the open source community is up in arms right now because it threatens the entire open source model. And at first, my first reaction was, that doesn't seem right. But then you remember, wait, no, we are talking about devices, not PCs. We're not talking about servers. And we're not talking about your PC or your phone. If the server goes down, we've got clusters and we can restart it and you've got general availability. We understand that problem. But if this is a device that's running your ventilator, if this is a device that's controlling the safety systems in your car, there's very different consequences. And maybe it does require a different bar. I don't know the proper name of it, but it's often referred to as the Biden Cyber Resilience Act. Also changes the rules. Australia just announced they're retooling their entire cyber legal framework. The UK is in the middle of it. You're right that we haven't seen a lot of response yet. The thing is, it's all in flight right now. All these legal frameworks are in the middle of changing, and it's basically going to be mandated that you're at the top of your game. And I think what I've read about the European one is a little smart. They're not saying this is what you have to do. They're saying this is the consequences if you don't.
Okay, final question. So we've got a lot of cybersecurity people in our audience. If they are working on a product team or working in a product development group, maybe on an IoT type device, and they're like, that sounds interesting, and they connect with Kry10 and learn more about your technology.
The fastest way is there's a little form you fill out on the website. So Kry10.com, KRY10.com, fill out a little form and we'll jump on that. The real thing you need to do is just think hard about your threat model and think hard about what is the complexity of the software on the device that you're building. As soon as you've got bits of software that have to be running mixed with bits of software that you want to update, that's a new pattern. And that's one we have to wrap our heads around. And that's like specifically what we're targeting. If this is a little ARM-M thing and it's doing one job and it's so simplistic that you're not worried about it, then that's a different conversation. But as soon as it becomes more complicated, then we would love to be there to help you.
And as you said, those more complicated, more robust, more powerful devices are becoming the norm rather than the
I think they'll
exception.
be more the norm than not.
Yeah.
Yeah.
Boyd Multerer, thank you so much for coming on and speaking to us on the Security Ledger podcast. It was really great talking to you.
That was great talking to you too.
We'll have to have you on again.
Okay, thank you.